we have to speak about what muscle architecture is. So muscle architecture is defined as the arrangement of the muscle fibers within a muscle relative to the axis of force generation. So you can appreciate in these figures that there are three different types of muscle architecture in three different muscles. For example, in the biceps brachii, the arrangement of the fascicles is quite parallel to the axis of force generation. Whereas in vastus lateralis, you see the classic pennation, which means that the fibers are inserted into the aponeurosis of the muscle with an angle defined as angle of pennation. And you can also appreciate that some muscle, like the gluteus muscle, present very more complicated and more differentiated muscle architecture. So skeletal muscle structure was also defined by Professor Lieber as the structural property of whole muscle that dominates their function. And I particularly like this definition because one of the things that comes to the eye when one starts diving into the muscle architecture world is that the architecture of given muscles are extremely consistent among individuals of the same species. So it's like that somehow the center constraints that exist in across species, within species, that actually dictate the muscle to arrange fascicles and fiber in that in that kind of way. But to understand what muscle architecture is in the practical aspect, we should look at an ultrasound image, for example. So this is the gastrocnemius medialis, and this is the soleus muscle. You have here the superficial aponeurosis and the deep aponeurosis, which are tendon layers that pack the muscle within. And you can basically see that here's a fascicle that runs from the deep aponeurosis to the superficial aponeurosis and is inserted in the muscle with a certain angle. So this will represent the fascicle length, this will represent the fascicle angle, and this distance, the perpendicular distance between the superficial and the deep aponeurosis will represent the muscle thickness, so the thickness of the muscle. So if you don't know, if you're not familiar with muscle architecture, so it's usually measured via ultrasound assessment, ultrasound scanning. You can also see a little bit of muscle architecture with some MRI sequences, and also you can measure three-dimensional muscle architecture with diffusion tensor imaging, which is quite difficult, but it is being implemented quite a lot in the recent years. Let's say in the last decade. I will not talk about the three-dimensional portion of muscle architecture just yet. We will touch it at the end of the of the presentation. But here you see that substantially you have a transducer. You place this transducer here on the skin. You try not to put a lot of pressure onto the muscle, so the muscle is not, of course, distorted, let's say. And you can see that you are placing the probe, which has to be parallel to the fascicle plane. So you see that my hand is holding the transducer, not completely, perpendicular to the muscle and not completely aligned to the longitudinal axis, but I'm aligned to the fascicle plane, which we say that has a pennation. And so I'm able here, of course, you probably don't see it, but you'll see it in the next picture. You see that I see, fascicles, and I see the aponeuroses that are quite parallel between each other. So if you take a good image of muscle architecture, for example, this is the vastus lateralis muscle, this is what it kind of should look like. You have two aponeuroses, which are quite parallel between each other. You have the muscle thickness, which is the measure of perpendicular distance between the two aponeuroses. You have the fascicle length here, and you have the pennation angle that you can calculate in different fascicles here along the deep aponeurosis. One thing that you should, notice when looking at this picture is that the fascicle that I decided to analyze here, you cannot fully see it in the field of view of the ultrasound, which was, I think, 5 centimeters for this one. So this probably, not probably actually, this actually represents a problem sometimes. So you can appreciate that here we have almost, as a percentage, we almost have the full portion of the fascicle within the field of view, and we're just extrapolating with manual linear extrapolation just a couple of bits from one side and the other side. But there are situations in which the field of view is restricted, so this is a 4.2 field of view, and the extrapolation is more. But also there are probes and transducers. For example, this is the makes me laugh every time I say it, but this is the Narici probe, which basically Marco had in his own labs, and we have it here in Padova. It's a 10 centimeter linear transducer that can allow to see the full fascicle, basically, or some full fascicles within the field of view. So this is still vastus lateralis, and this is vastus lateralis obtained with a 4.2 centimeter. So remember this extrapolation problem, because we will talk about this later on in this talk. So when we talk about muscle architecture, we cannot refrain from discussing also physiological cross-sectional area. So anatomical cross-sectional area is represented by the area that you will obtain, or one will obtain, if we cut the muscle completely perpendicular to the axis of the muscle. In this case, physiological cross-sectional area is defined as the cross-section that cuts all the fiber at the right angle. And you can appreciate, we will not go into the trigonometry and into the calculation, but you can appreciate that fiber length and pronation angle are involved in a calculation of physiological cross-sectional area, so in the equation. And physiological cross-sectional area is important because it's related to the maximal force production of a muscle. So this was a very elegant and quite old now study in which the authors estimated physiological cross-sectional area from some calculation and measured actually directly on Guinea pig's muscle physiological cross-sectional area, and they showed that the estimation of cross-sectional area and the measured one were fitting a good line of identity. But they show basically also that the maximal tetanic tension that was produced by PCSA was related also to the physiological cross-sectional area itself, so to the quantity. And to appreciate what physiological cross-sectional area does to the two main relationship that we can observe in skeletal muscle, so the force length relationship and the force velocity relationship. So if we assume that we have two muscles with similar fascicle length, similar pronation angle, similar distribution of fiber type, and similar output of force per muscle unit, but different PCSA, we can appreciate what physiological cross-sectional area really means. So in a muscle with a small PCSA, the maximum tetanic tension produced will be around 50, for example. But in a muscle with a large PCSA, the maximum tetanic tension could be almost the double, let's say, but while maintaining the same force length relationship. And here, similar force velocity relationship is seen, as in, you can see that the maximal velocity of shortening and the minimum velocity of shortening, so isometric, at the isometric state, is similar between the two muscles, but the muscle with the large PCSA will produce more tetanic tension, more tension for a given point of the muscle velocity, for muscle velocity. And fascicle length, so not only physiological cross-sectional area is variable between muscles, but also fascicle length is. And if we instead consider two muscles with the same physiological cross-sectional area, but with different fascicle length, so we will see how this fascicle length difference will affect the muscle force velocity relationship and force length relationship. So the maximum tension will be similar, but the properties of the muscle excursion will be different. And here you will see that the velocity of shortening will be affected as theoretically is increased in fibers with longer fascicle length. So to summarize up to here, muscle architecture in theory can really influence the properties of skeletal muscle, physiological cross-sectional areas related to maximal force production, fascicle length to the velocity of shortening of a muscle. So particularly like this slide, I used it in another presentation previously, but makes me laugh, especially the cat makes me laugh a lot, but this is just to, break the ice. Sorry if I was boring, but we had to talk a little bit about muscle architecture before moving on. And by moving on, we need to introduce the concept of muscle plasticity. So muscle is highly plastic, is a highly plastic tissue, and you can appreciate how muscle modulates itself and regulates like its shape and its structure in acute states or in chronic states or across lifespan. For example, this is an elegant figure that was presented by Goldspink in a review in 1985, and this is related to the addition of or loss of sarcomeres in series in mice in mice muscle. So you can see that when the mice is born, it starts adding sarcomeres in series. So during the development stage, so basically elongating fascicle length as well by addition of sarcomeres in series. But if we immobilize a muscle of a young mice by a cast, you can see that the addition of serial sarcomere is impaired somehow. But it then is restored when the cast is removed, and actually in a very quick time, you can see similar slope here. It goes to it comes back basically to the point of young muscle of a young mice that has basically stabilized the number of sarcomeres in series. But then again, in adult muscle, if you place a cast in lengthened position or in shortened position, you have either an addition or loss of sarcomeres in series, which is quickly restored if the cast is removed. So this figure fully, makes me appreciate the real concept of plasticity of a muscle during lifespan, and if certain constraints are, in this case extreme constraints, are put on or are applied on the muscle itself. And something that you can appreciate talking about muscle architecture in a situation across lifespan, you can see that in a young male, a 27-year-old, pennation angle is quite bigger than compared to an older male, 73 years old. Of course, muscle thickness, so the muscle the size of a muscle, so the dimension of a muscle is bigger in a younger person. But you can also see that possibly fascicle length will change also because of the reduction of muscle thickness. Although we have also a reduction of pennation angle, so fascicle length will have to be checked. But this is to appreciate that once again how muscle plasticity is highly influencing muscle architecture across lifespan. And something that we can say as well is that when you train, so you apply a mechanical stimulus to the muscle usually responds by starting an hypertrophy journey, if we can call it like that. But also muscle architecture has been shown to adapt very, very early in a training program, in a training regime. And that you can see that fascicle length has been shown in this elegant study by Olivier Senes, has been shown to change already after 10 days, okay, of, in this case, was isoinertial leg extension, I suppose, because this is a yo-yo system, yeah. But you can also see that after 20 days and 35 days, you can fully appreciate the fascicle length and pennation angle and CSA, so hypertrophy, were completely, modified. And this shows that muscle architecture and muscle morphology can adapt very, very early to a training situation. We will be back to the training concept, but now I also want to focus a little bit onto the other aspect, so the other side of the of the story, which is unloading. So another elegant study, in my opinion. Really always liked this study since the day I was a master student. You can see that already 14 days of unloading, so in this case, unilateral lower limb suspension in young men, creates a 5% decrease in muscle CSA. I think we're talking about, I'm pretty sure it was vastus lateralis in this case. If it's not, I will be ashamed of myself because I said that I like this paper too so much, but I think it's vastus lateralis. And you can see that there's a relative decrease also in torque, Young's modulus, tendon stiffness. But look at the muscle architecture. Muscle architecture, there's a change after 14 days in pennation angle, so a decrease significant, and there's a significant decrease also in fascicle length after 23 days of unilateral lower limb suspension. So adaptations to loading occurs very early, but adaptation of unloading as well, and in my opinion, even with a high velocity, because look, already 5% of CSA lost, okay, in after 14 days, and we're close to the 10% after 23 days of unilateral lower limb suspension. So unfortunately, we are all experiencing a bad moment for, let's say, humanity and the world itself, and we are all, facing the COVID-19 outbreak. And so, for example, I'm talking about Italy, but there's many countries that had to endure a home confinement, so a lockdown period. And during the lockdown period, with some scientists and athletic trainers, we asked ourselves, so what is going to happen specifically right now to elite athletes? And I started thinking about all these, papers that I read, like in physiological papers of unloading of skeletal muscle and tendon adaptations. And I said to myself, okay, is this a model that we can use to predict what is really happening? Not quite, but at least we can take some good, aspects out of it. So, of course, what we all experienced in the home confinement, was not obviously fully unloading condition. And it was not really completely the training itself, because some of us started training. But if you talk about athletes, elite athletes, they surely had the possibility to implement some training, in the home space. But how this can work like in a model in which we have to understand during home confinement what really was happening. So let's say that elite athletes received training programs from clubs, from trainers, and trainers were very good at acting straight away in this direction. But let's say that I'm a very successful player, and I have a possibility to have a gym in my house. My house is big. I have like a big garden, and I can train, so I can implement the training program that the club and the team gives me. But at the same time, I can do stuff also with myself, like with my personal trainer. And let's say that on the other side, maybe I am not completely successful player and I'm still working in elite sports, like still playing, and I don't have like as much equipment. So how did this, like play up? Um, and also what I thought it was, so there's a loss, there's a lack of specific stimuli. So for example, let's take football players. Football players didn't see the pitch, for quite some times, and so they couldn't jump, run, make change of directions, like and so how this was, how this plays up like at the end when we have to come back, when when the elite athletes had to come back to training. This has just been accepted and will be out soon. I decided to not show the figures because I was just involved in this kindly involved in this work by Daniel Cohen and Matt Habener, but actually something that we saw in this case, and it was with the America Cali Football Club, and then what we saw is that there was a reduction, not in the jump height, for example, in the counter movement jump, but in some aspect of the yielding eccentric phase or the landing eccentric phase. So this tells a little bit about some neuromuscular qualities in elite footballers during COVID-19 quarantine and the change. But I assume that probably some architectural aspect, morphological aspect, and mechanical properties of either muscle and tendon were potentially responsible for some of the changes that we've seen. Unfortunately, we did not have ultrasound, we did not have any MRI, so we cannot claim this, while we can just speculate. But what I can show you is that, so I'm preparing a little review on this because it was, it was in my mind the whole quarantine, and this is just to let you understand that a lot of the literature that is investigated, that has investigated detraining, show a lot of changes in fascicle length and pronation angle, mostly decrease in different muscle groups, in different muscle of different muscle groups. I just want to show you one thing, which is, in my opinion, very peculiar, and it's something that I'm working on at the moment. Look at the biceps femoris long head. There's always, in a detraining situation, an increase in pronation angle rather than a decrease in pronation angle that is seen in other muscle. So I don't know why. Literally, I don't know why. I ask myself, and maybe it's a peculiar muscle that responds in a peculiar way to detraining that I don't know. I do not want to speculate because literally I have some clue, but I don't want to speculate too much. All I'm going to say is be careful when you see some of these data, because they were conducted with the ultrasound methodology that has a limitation. But at least, a decrease in pronation angle was seen, and with even if the field of view was restricted, and for fascicle length there are some problems, for pronation angle we should trust this data possibly. Anyway, just to let you understand how muscle architecture changes rapidly, also, for example, an injury, after injury. So this was following acute Achilles tendon rupture. I mean, I don't have to speak, okay? Maybe the ultrasound here is not completely clear, but I don't have to even show you anything. You can see that pronation angle increases so much in the injured limb, and that fascicle length is highly reduced. And this is possibly because there's of the interplay between muscle tendon unit, between muscle and tendon. When the tendon is releasing the muscle has to readapt very, very rapidly because muscle wants to somehow preserve itself. But this was just basically to show you that not only we have great changes during the training, and we have also great architectural changes during after injuries. And to come back, so we will look at the unloading, the detraining, and the injury aspect. To come back on the training side, so we have studied in the last decade, so in the last years, what happens to the muscle when you give either eccentric or eccentric stimuli. So just to let you show, this is the behavior of the vastus lateralis. I hope you will come back. Of the vastus lateralis on a leg press exercise. This is during the pushing phase, okay? So you can appreciate that there's a tilt in pronation angle and a shortening of the fascicle. And then during the eccentric action, so during the lowering of the load phase, you can see that pronation angle doesn't change too much, but there's a sort of a elongation of fascicle. And it was probably not rocket science, but when you apply these two different mechanical stimuli for 10 weeks, this is what you get. Similar amount of hypertrophy reached by eccentric and concentric training, pure eccentric and pure concentric training, but kind of like different strategies of muscle architecture adaptation. So fascicle length was increasing greater after eccentric phase, and pronation angle increased greater after concentric phase. So this is a figure I put together for a review that I wrote in 2017 on eccentric and concentric contraction. And I'm not completely fully convinced about this right now because I started to re-change my mind a little bit. But actually, what I can tell you is that if you have an increase in the size of a muscle, for example here, it can be reached by an increase in pronation angle, which kind of reflects the addition of more sarcomeres in parallel, and potentially also an increase in fascicle length, which in theory, from some of the animal studies, should reflect the addition of sarcomeres in series. By re-looking at the literature and by looking at some of the latest science, we can also say that potentially this is related or could be related to not only an addition of sarcomeres in series, but also to a lengthening of the optimal length of the sarcomere, or to both, let's say. We have a study that will probably come out soon, or well, I don't know if it's going to come out soon, but we're ready to. We're preparing it with Stanford and Professor Glenn Litwork that will show some of these insights very soon in humans. So more on that another time. But just to also speak about the other side of the story, that not all the people that looked at concentric and eccentric contraction showed a greater fascicle length change after eccentric exercise. So Professor Blažević in 2007 showed a similar increase in fascicle length between the concentric and eccentric exercise. And here it's one of the latest reports that shows that maybe with accentuated eccentric load compared to traditional load, maybe intensity or the intensity, so the strain applied to the fascicle is maybe key, but more on that in new research. So when we have to talk about architecture and function in vivo, we have to basically see what's out in the literature. This is a study that shows that basically the sprint time was related, so less sprint time was related to bigger muscles, so bigger volumes. And it's not the first study that shows that muscle morphology is related to performance capacities. So this was fascicle length related to 100-meter personal best record. So the higher the fascicle length, the greater the fascicle length, the shorter, so the time to compete 100 meters. And you can see also how pronation angle is different if we look at the pronation angle of bodybuilders. Apart from the curvature, look how big is the pronation angle in respect to normal muscle. So this tells you a little bit that performance is potentially related to skeletal muscle architecture. And this was another study by Tony Blažević and colleagues in JAP, in which it was shown that the fascicle length changed when basically pulling together fascicle length change from a concentric and eccentric group. And comparing them to the torque angle relationship, you can appreciate that fascicle length changes go hand in hand with the changes in the torque angle relationship. Conversely, in a later study, Tony showed there was no relationship between the shift in angle torque relationship and fascicle length changes when training muscle isometrically at shorter lengths and longer lengths. So there were regional increase in fascicle length, but they were not related to any shift in the angle torque relationship. So why do we see some reports that say the muscle architecture does influence performance or muscle properties, and others that doesn't show that? It's because it's a complex interplay. There's not just one player here. There's not just a fascicle player here. First of all, the changes in static muscle architecture are usually measured at one muscle site. And how does muscle architecture behave during a dynamic task? Is it only something related to PCSA, pronation angle, fascicle length, or there's more? What about the constraint the extracellular matrix give to the architecture, for example, in its remodeling? And what about the series elastic component or muscle gearing, so the rotation of muscle fibers during contraction? So you can appreciate that there's a complex interplay here. So if I'm going too long, please tell me, because I know I can talk too much. So just to let you know, and please let me know. But I wanted to give you also an example of what we can do in the applied world in order to not fully, but in order to appreciate muscle architecture, in order to measure it. So I'm going to talk a little bit about the biceps femoris long head muscle. Well, the reason I don't have to tell you, guys, but it's one of the muscle that is injured the most, and you know, from a structural point of view, from an architectural point of view, there's a very complex architecture and very inhomogeneous architecture across the whole length of biceps femoris. But so one of the theory that of the injury, or let's say of biceps femoris, is that if biceps femoris has a shorter fascicles, so we'll have potentially shorter material that is in series, so a lower number of sarcomeres in series, let's say. And one of the theory that was proposed by Ryan Timmins was that if I elongate the fascicle, if I put more material in series, then I will be able to have a fascicle that can sustain strains a little bit better and produce forces, higher forces at longer muscle lengths as well. So to have a sort of a, let's say, protective, effect of lengthening these fascicles. And a lot of the literature that is out, not just on biceps femoris now, but before on muscle, on other muscle, shows that if you apply lengthening contraction, so the lengthening stimulus and the strain, the muscle architecture results in increasing in fascicle length. So basically what happened is that the Nordic hamstring exercise was revised, basically, and now we know that Nordic hamstring exercise, when it's included in training programs, it does give benefit to the player, because the injured seems to be reduced, the injury rates, when you include Nordic hamstring exercise. And essentially, Nordic hamstring exercise was seen as a mechanism, or as a way, like to apply eccentric loading, so to apply the eccentric strain and fascicle lengthening at higher forces, okay, with higher forces. So in order to create an adaptations in fascicle length, and in order to have basically bigger amount of sarcomeres in series added to the muscle. So there's a bunch of literature that shows that this happens, as in that the fascicles are elongated, not that sarcomeres are added in series, but this is thought to happen. But there's a little bit of a problem with a lot of studies that have been conducted on muscle architecture and biceps femoris long head. So biceps femoris has a very inhomogeneous architecture, and when we go and place the probe here on this muscle right here, if we have a small field of view, which is about 4.4, 4.7 centimeter, what happens is that we have to extrapolate this fascicle right here. And you can see that it's a very big extrapolation compared to what we see. So we don't know if there is an aponeurosis curvature that is happening, and it's quite likely that there is, okay? And also we don't know if the also change a little bit of curvature. And I can show you this pattern here is not unusual for biceps femoris. So you can appreciate that we have a problem here. I mean, the studies were conducted with the right ideas, but the methodology used was not completely was not the best one that was used, but it was the best that it was at the time. So that I know. So when you have instead the opportunity to do panoramic scans of biceps femoris, you can appreciate that something that looks like this from a restricted field of view is not what you see when you have a higher, a larger field of view. And you can appreciate that fascicle, tend to curve, and aponeuroses tend to curve. And so we don't really know if what we see here is what we can measure completely here, right? So we went to look at this in a cohort of the Swiss skiing national team, and what we found is that the trigonometric equation that was used to extrapolate this fascicle, dependent from the muscle thickness, the angle between the two aponeuroses, and the pennation angle. So the trigonometric equation that was used in most of the study somehow overestimated the fascicle length by quite a lot when compared to manual linear extrapolation, another trigonometric equation, and the extended field of view, so the panoramic image that I showed you. And if you look at the Bland-Altman plots that were run between the equation A and extended field of view, you can appreciate that not only there's overestimation, but in some cases there is underestimation. And this is, I'm not going to go like fully into this, but it's dependent on the changes mostly in the angle that is between the aponeuroses when you measure, and also the changes in pennation angle. So we have to be careful, because sometimes what we cannot see is not really what happens in reality. So extrapolation becomes a little bit of a problem. And actually, this is the first time I'm presenting this. These are preliminary results from a 10 days bed rest study. So we looked at the changes in biceps femoris long head fascicle length, because I thought it was quite interesting from a clinical point of view, and I'll explain you why in the next slide. But what we showed here is that if you use the panoramic method or the manual linear extrapolation, you see a little but significant reduction in fascicle length after only 10 days of bed rest. Okay, but the trigonometric equations do present some problem, and especially probably because of what I said to you before. It's dependent on an equation, and it brings in extrapolation, and it's not ideal basically to use possibly that method even when we monitor longitudinal changes in muscle. And why? But anyway, one thing that I want you to appreciate as well is that 10 days of bed rest creates, also I didn't present the CSA data, but there is a substantial, there is a decrease in CSA of the biceps femoris long head only after 10 days of bed rest, and also you can see the change in fascicle length. So this is important for clinicians because, of course, the people will not be in 10 days of bed rest usually, or athletes are not. But what happens after a surgery? So this is quite important to understand that usually if we implement, early rehabilitation, for example, we will be able to have an earlier return to sport or earlier recovery. And this is something that I want to pass on. Maybe now we can have the right tools, but so far we have not used them maybe in the best way. So my suggestion is people like me that study physiology and study things in a laboratory, we should do maybe more complex studies in order to translate the findings onto the translational aspect, onto the applied settings. This is better for me because I can tell you something that you can trust. And I think we should somehow diminish the study in which we just like put a probe on, we see something and we make an association. I think or at least one of my goals is to try to go and really unravel this from a physiological point of perspective. And this will be better for us and better for the prediction in the long run. And at the end of the day, even there's not much evidence that architecture is related to function in vivo, muscle architecture are frequently seen in unloading and loading scenarios, right? So in my opinion, why? I mean, I ask myself, why do we see this? Is it related really to function? But why should a muscle change like that? Is it only biology or physics? I think the form follows function. For now, I'm a believer. In the next years, I will let you know.